Hello, you're welcome. All right, so now we're going to be looking at a very important topic in physics, and of course, that will be the very first topic, right, in this series, and of course, and that is measurement and unit. Okay, right. So now, measurement is very vital in physics. In fact, practically every laboratory procedures actually requires measurement. All right. And the question is, what is measurement? Right now, measurement in physics is an act of finding the size of a physical quantity. Right, measurement is the act of finding the size of a physical quantity. And now the question is, what are physical quantities? All right, physical quantities are quantities that can be measured. Okay, any quantity in physics that can be measured, length can be measured, it's a physical quantity, mass can be measured, volume can be measured. So any quantity that can be measured are regarded as physical quantity. And now classes of physical quantities. Now these physical quantities are being classified. They are of three types. Okay, you can just classify them of three types. And um they include, we have the fundamental quantities, the derived quantities, and vectors and scalars. So in the scope of this tutorial, okay, we're just gonna deal with these two, the first two, which is fundamental quantities and derived quantities. Now vectors and scalars is gonna be a topic on its own. Okay, so we proceed. Now we'll be taking the notes, okay, from a book, then I paste it on the board. Then of course, if we get to a point where I need to illustrate, of course I will illustrate here on the screen. So now let's actually proceed. So now we have the we have these two, so we're gonna start with the fundamental quantities. Okay, so I pick the notes, then we illustrate it. So fundamental quantities, here we go. All right, so I bring it up. So now the question is, what are fundamental quantities? Okay, so as the name implies, fundamental quantities are quantities that provide the basic unit of measurement. Okay, fundamental quantities form the foundation in which other quantities derive their definition. So they are the foundation. The other quantities depend on them. Okay, they are independent. So they are the one that form the foundation, and they provide the basic unit of measurement. Okay, so that means in physics, every formula you ever encounter, every formula, okay, has its roots from a fundamental quantity. And you need to know excuse me, all the fundamental quantities. Okay, you need to know them as a physics student. So all fundamental quantities in physics are listed below. We have mass, length, time, temperature, electric current. I'm gonna still, there's still more, so let me bring them up. Okay, here we go. Okay, so I'll bring it up. So there are seven of them. So here we go. So we have mass, length, time, temperature, electric current. Then we also have uh, amount of a substance, luminous intensity. So all are being represented by symbol. Okay, let me go again. We have let me use the symbol. We have the length. Okay, excuse me. You have the length, which very important, which of course we represent by the length, by L. We have mass, which we represent by M. We have amount of a substance, which we represent by capital letter A. Okay, we have length, mass, Also have a temperature, time, very important. Okay, but this is the most important: length, mass, and time. All right. Then of course every other thing we've actually mentioned here. All right. We have amount of a substance. We have luminous intensity. Luminous. Okay, so we have 7 of them, so you can just go through them again uh, and make sure that you remember the 7 fundamental quantities, because every formula you're going to encounter in physics, okay, has its root from the fundamental quantities. All right, so please take note of them. Okay, so now the next we're going to go to the derived quantities, right? So what are the derived quantities? Okay, now of course, as the name implies, every derived quantity is being derived from the fundamental quantity. Okay, all right, so let's go there. Now, derived quantities. These quantities are gotten by combining 2 or more fundamental quantities in a formula. All right, so as I said, every formula you ever encounter in physics, okay, is being derived from the fundamental quantities. So now let's look at them one after the other. Okay, example. Okay, speed is actually speed is a derived quantity that is derived from distance all over time. Okay, distance divided by time is speed. Okay, of course, distance is can also be measured by length between 2 points. All right, so that's length all over time, L all over T. Velocity is displacement all over time. Okay, which is, of course, displacement is also measured in length between 2 points. Now, the difference between velocity and speed, since they are all measured in length, is that for distance, which is a scalar quantity, it doesn't have direction, but displacement is a distance in a specified direction. So please take note of that. Okay, this is a scalar quantity, while this is a vector quantity, right? Please take note of that. But apart from them having direction, they mean the same thing. All right. Apart from one having direction, okay, and the other doesn't have, they actually mean the same thing. Then you now have acceleration. Acceleration is given as velocity all over time, okay, which of course is length all over time square. Of course, you can know how you see how that is being derived already. Since acceleration is velocity all over time, and we know that velocity is equal to length all over time, then divide by another time. Okay, this time t times t will give you t square. So that is why acceleration is length all over time square. Okay, so please take note of that. Then we have force. Force is actually a derived quantity that is derived from mass and acceleration. So force is equal to mass times acceleration. Then you have work. Work is force times distance. All right, so those are basically, there are a whole lot of them. As I said, practically all the formula in physics, okay, are actually derived. They are derived. Okay, so please take note of them as we proceed. Okay, so let's go to the next subtopic. Now, what is the next subtopic? The next subtopic is dimension. All right, so now let's go there. Now, what is a dimension? Okay, now dimension in physics, okay, dimension of a quantity is the size of the quantity measured from the fundamental quantities, okay, which make up its formula. Okay, so we can say that every derived quantity, which of course we know has a formula, and those formula are gotten from the fundamental quantity, have that is can express in dimension. So the dimension is simply those symbols. Okay, the dimension of the quantity is actually the size of that quantity measured from the fundamental quantity, which make up its formula. Okay, so in dimension we use symbol of fundamental quantities. Okay, and of course those symbols are written in an uppercase, right, to represent the formula. Now let's actually look at this. Okay, for the symbol, anytime we see mass, okay, in dimension we use capital letter M to represent mass. So if that particular formula, okay, has mass in dimension, we use capital letter M to represent it. Now, length we use capital letter L, time we use capital letter T to express those formula. Now, we're going to look at example, okay, typical example of our dimension, so that we'll solve it. Okay, I have a question here, and then I'll bring it to the screen. Here we go. Bring it to the screen. Okay, so now the question is this: express the flowing in dimension. Okay, so the very first is first express velocity in dimension. Simple. All I just need to do is to express the formula of that particular derived quantity, okay, using the symbols of dimension. All right, so now let's look at it. Velocity, we know it is given as distance all over time. All right, and of course distance is measured in length. All right, and that's capital letter L. Dimension, distance is length is capital letter L, then all about time. So, and of course time is capital letter T. And of course, in dimension, we express our answer not in a fraction, but in an initial form. Okay, so we simply means that the denominator of this fraction, I'm going to take it up. Okay, so that, and once I take it up, it's going to be converted to a reciprocal. And what's the reciprocal? It's going to be LT raised to the power minus 1. All right, that's reciprocal in indices because it has gone up. Right, it becomes LT raised power, because here at this point it's T raised power 1, T is same thing as T raised power 1. So if the T goes up, it becomes T raised power minus 1. So please take note of that. So this is A part of this question. All right, so now let's look at the B part of the question and solve it. We have acceleration. Remember, I told you that acceleration, okay, is velocity all over time. All right, so now putting that in dimension, we have already evaluated for velocity. Velocity is giving us LT raised to the power of minus 1, and of course T raised to the power minus 1. All right, capital letter. All right, so you know what's going to happen. This T raised, oh sorry, just T, so I made a mistake. There's velocity all over time, so velocity is T LT raised to the power minus 1, then divided by time, which is just capital letter T. So what happens is this T will still have to go up. All right, okay, so I'm gonna have LT raised to the power minus 1, then times T raised to the power minus 1. All right, and of course in indices, T raised to the power minus 1 times T raised to the power minus 1 will give me T raised to the power minus 2. Okay, indices, since powers will add each other because of this multiplication, the powers will add. That will be minus 1 minus 1, okay, which gives me minus 2. So please take on this the dimension of acceleration. Okay, so then we have the next question, which we are being asked to evaluate the dimension of force. All right, force in physics, you need to know the formula. Of course, force is given as mass times acceleration. All right, that's the formula of force, so we can put it in dimension. The dimension of mass, of course, we use capital letter M to represent mass, and the dimension of acceleration we just did that, and that gives us LT raised to the power minus 2. All right, so as easy as that. Then now we proceed to do the last but not the least. We have force, sorry, work. All right, the dimension of work is force. The formula of work is force times distance. Okay, force times distance, we use S to represent distance in physics. All right, so force, we have actually evaluated force. Okay, so we just write the dimension of force, that's MLT raised to the power of minus 2. All right, then times distance, which of course is being represented by L. So when I have L times L, gives me L square, so I'm gonna be having ML square T raised to the power minus 2. That's it. Okay, I hope that is well understood. All right, so we move. Okay, so the next thing we got to do now after evaluating question dimension is we're going to look at what unit. Remember this is measurement and unit. Okay, so now let's look at the part that has to do with unit. All right, so I bring it to this screen. All right, so here we are. Now, unit of measurement. Now, all quantities have units, okay, used for their measurement. In physics, the general accepted unit of measurement is called the System International Unit. Okay, that's what there is abbreviated as SI unit, System International. All right. Now, of course, anytime you take measurement, okay, there are two things your measurement will give you. Okay, the value of the measurement and the unit of the measurement. Let's say the value of the measurement, okay, or the quantity of the measurement is 20. Okay, now for someone to know that this 20, what you measured is a particular quantity, you must put the unit. For example, if the measurement is 20 meter, okay, it's not the same as 20 newton. 20, once I see meter here, I know that what the person measured is length. Okay, if I see newton here, I know it belongs to force. Okay, so definitely every measurement has unit, okay, that is actually used for each measurement, and that we're going to be looking at them. Okay, so for the fundamental quantities, we use fundamental units, and for the derived quantities we use the derived unit. Okay, so let's actually look at them. We're starting with the fundamental quantities, okay, and their units. So we get a table. Okay, okay, we got a table, or we just, okay, let's get all right, here we go. Excuse me. Okay, so I bring it to the screen. Here we go. So now for the fundamental quantities, okay, which we know, right? So let me, for the fundamental quantity, let me just write that on the board. Okay, we know that we have mass as a fundamental quantity. Okay, so the unit of mass is kilogram. Okay, which is abbreviated in what? Kg, kilogram. Okay, so kg. For length, okay, the SI unit of length is meter. So let me use symbol here. Okay, so meter m. Time is measured in seconds. All right, okay. We go temperature. Okay, temperature is measured in Kelvin. Okay, Kelvin. All right, so going forward, electric current. Electric current. Okay, is measured in ampere. All right, then you have luminous intensity measured in candela, right? Amount of a substance measured in mole. All right, when you go through the textbook, you have all this list. All right, so please take note of that. Now let's look at the one of the derived units. Okay, look at the derived unit. Okay, I think I've seen the table I'm actually looking for. I can bring it to the screen. Okay, the table I'm looking for. All right, here we go. Okay, so we go. So this is the quantity, the derived quantities, right? The fundamental quantity. Length is measured in meters m, mass is measured in kilograms, so time is measured in seconds, current is measured in ampere, temperature is measured in Kelvin, K, amount of a substance is measured in mole. Okay, luminous intensity is measured in candela, so please take note of that. All right, so now we now move to the derived units. Okay, derived units. So we just take some of the derived units and of course explain them. Okay, so here we go. I put it on the screen. All right, so this goes like this: derived quantities. Okay, this is derived quantity, and this is the formula of the quantity, and this is the SI unit. For velocity, we know that velocity is displacement all over time, so which of course the unit is meter all over seconds. Please take over meter per second. That's how you pronounce it. Acceleration, okay, is meter per second square. That's the SI unit. Force is measured in Newton. You should know that already. Okay, work is measured in joule. Then power is measured in watt. These are their SI units. Okay, so there are some of them. The SI unit is just given after the name of the person that participated. Okay, and creating the formula of that particular quantity. So that's why you have work joule, power watt, and of course force Newton. All right, instead of their derived units from the formula. Please take note of that. Okay. So here we go. We proceed to the next. Okay, we have density. Density is measured in kilogram per meter cube, and of course pressure is measured in Newton per meter square, because pressure is force all over area. Okay, force all over area. Force is measured in Newton, area is measured in meter square, so pressure is Newton per meter square. So just anytime you are actually working on formula, all right, what you should do is for you to first know the unit, okay, that you're working on, and of course how it is being derived. Okay, so here we go. So the next subtopic we go. So now the next subtopic we're going to be looking at the sub-multiples and multiples of a unit. Now we know that okay, SI unit actually uses one. Okay, actually specify one unit as a standard. That doesn't mean there are not other units. Okay, for example, we know that the unit of length is meter. It's obvious, but meter is not the only unit, okay, that we have in length. Okay, we have centimeter, lower unit. We have lower unit from meter, that is we have the centimeter. Okay, we have the decimeter, they are lower. We also have even the higher limit of length, which of course kilometer. Okay, but SI unit chooses what? Meter. So now we're going to look at a kind of conversion. Okay, let's look at all the sub multiples and the multiples. The sub multiple of units, okay, the smaller factors of a unit are called the sub multiples. Okay, the smaller factors of a particular unit is called the sub multiples. All right, and how do we convert? Now let's look at how to convert. Conversion of sub multiple units are shown below. All right, now this is going to be a kind of table, right? It's a table. We have a table here. All right, let me put that. So this is a sub multiple name, and of course this is the conversion factor. This is how you convert it. We'll take it one after the other, right? Okay, anytime one of the sub multiples of a unit is micro, anytime a unit is micro, like example micrometer, okay, micro simply means that you are dividing that unit by 1 million. That's one sub multiple. Okay, you are dividing in sub multiples. If you want to convert someone to, you divide. Okay, so for example, if I have 1 micrometer and I want to convert 1 micrometer, okay, I simply need to convert it by dividing by 1 million. That's 1,000,000,000,000,000. The zero is 6 times, or I multiply that 1 by 10. Okay, let's power minus 6. 1 divided by 1 million is something as 1 times 10 is power minus 6. Okay, so please take note of that. Okay, let's get more of them. Let's get more. All right, so here we go. So please take note of that. For micro, we are looking at okay. So now let's look at this. Then now the next is milli. As you can see here, milli. Okay, so if you're looking at milli, okay, if you're converting milli, you're dividing by 1000. For example, 5 millimeter. All right, let me go to this. Let's say you're being given. Let me clean up. Let's say you're being given, okay, 5 millimeter is milli, okay, to convert to meter, right? All you need to do is to divide the 5 by 1000. That's what milli is, okay? So milli in meter, you're divided by 1000. It can be millinewton, it can be any unit. This one here is the sub multiples, while this one is a unit, okay? So this one it can be anything here. They can be like millinewton, okay? That means you're converting the millinewton to newton, okay? It can be any, so please take note of that. So you're divided by 1000, all right? And of course, if you divide 5 by 1000, you have 0.05, right? And of course, now it's going to be meter. So please take note of that. All right. So that's milli. Okay. Then we still get more of them. See, get more of them. Here we are. Okay. Okay. See, get more of them. Okay. So yeah, these are multiples. I'm not done with these sub multiples. Okay. Okay. Sub multiples is running, and the multiples. Now let me take it along with the multiples, right? Okay, so here we go. All right. Okay, so now we actually looked at all right, here we go. So we have centi. Remember, we talked about milli, okay? Now if it is centi, you divide by 100. If it is deci, you divide by 10, okay? So please take on that. Now the multiple, all that I've mentioned so far, the micro, the milli, the centi, and the deci, micro, milli, centi, and deci, okay, they are all some multiples lower. Those one are lower factors. Those one you convert them by dividing, okay? So now we have the multiples of the unit. Right here, the multiples of the unit are the larger factors of a unit, okay? Now the table below are correct, so some multiple factor of units. So now we have kilo, okay? Kilo. Anytime you're converting in kilo, you're multiplying by 1000. Kilo is 1000 multiplied by 1000. Mega is multiplied by 1 million. Y giga, you're multiplying by 100 million, okay? They are all increasing by a factor of 3 decimal places, okay? Now to illustrate this, I think I'm going to bring an example so that you will get it proper. All right, so here we go. I will import an example so that we can illustrate this proper. Okay, so I bring it to my screen. Okay, I bring it to my screen. Okay, so here we go. Convert the following units to meters. Okay, so this is for meters, right? Solution. All right, so if we are being given, I'm starting with a part of the question, okay? Now I'm being given a to convert 20 millimeter. I want to convert 20 millimeter. All right, remember, if you want to convert milli to meter, okay, you divide the 20 you want to convert by what? 1000. All right, you divide it by 1000. All right, so if we do this cancel, that's 2 divided by 100. That will give 0.02. So 20 millimeter is something as 0.02 meter, right? When you convert it, all right. So now let's go to the next question B. 5 cm to meter. To convert from cm to meter, you divide by 100. So please take note of that. To convert from centi, okay, you divide by 100. That's 5 all over 100, okay, which gives us 0.05 in meter. All right, so that is B. Then of course C, kilo is multiple and you're multiplying by 1000, so 10 kilometer, right, is, if you want to convert it, is something as saying 10 then times 1000, 10 times 1000, okay, which of course is 10,000. So 10 kilometers is something as 10,000 meter, 10,000 meter. Then of course we now have cm square, all right, 3 cm square. Now cm square means it's telling you that what you're converting must be squared, okay? So anytime if you convert it, you must square it for it to be complete. So the first thing I need to do is just to convert the cm first to meter, right? Which of course that'll be 3 divided by cm to meter is 100, okay? But remember the unit is squared, so I see how to square it. All right, so what's it gonna be? This, if I divide this, I'm gonna have 0.03, okay? Then don't forget the square, I square. All right, and of course when you square, you have 0.0003 meter. Okay, so I hope that is well understood. And of course, the last but not the least, cube, 10 cm cube, 10 cm cube. Okay, so if you want to do this, you convert the cm to meter first, right? Then of course you cube. So this, when I do this division, I have 0.1, right? And when I cube, I'm gonna have 0.001. Okay. All right. So, if I'm not mistaken, right? I'm not mistaken, I believe. Okay. So that's just by the way. Now, there's one thing you should know about this conversion. Okay, if you're converting from right to left, just like you're converting millimeter to meter. All right. See, you are dividing, but a situation where you're being given meter, okay, to convert back. If you are converting in the opposite direction, okay, back, you are multiplying, okay. For example, if you are being given 0.02 meter and they say convert to millimeter, remember it is only when you are converting to millimeter to meter, okay, that you divide. Then if you want to convert from meter to millimeter, then you multiply, okay. So it's vice versa, so please take note of that. All right, so I hope that is well understood. Okay, let's still so proceed to the next topic. So having learned the measurement quantities, which of course is the fundamental, the derived quantities, of course, the dimension. All right, so we are going to go straight to the measuring instrument. There is no measurement without a measuring instrument. Okay, you take measurement using measuring instrument. So we are going to look at some of these measuring instruments, okay, in physics, and of course how they operate. All right, so let's talk about this measuring instrument. Now each one we are going to be looking at, okay, each one we looked at, we are going to each of the quantity we are going to consider. We'll consider the measuring instrument that is used for each measurement. So I get the notes and I bring it to the screen. Here we go. Okay, so we are starting with length, the measuring instrument of length. Measuring instrument of length, okay? Length is a distance between 2 points, okay? It is measured in meters. This how you talk that is meters. Now, depending on the magnitude of the length, okay, the accuracy or the precision needed for that measurement, okay? So we will be looking at different measuring instrument is actually required, okay? So if you are the length, the magnitude of the length, okay, that you want to measure, the precision you are looking at, okay, and the accuracy you're going to look at will require different instruments. So we're going to be looking at the instrument one after. We'll start with the very first instrument, and that's a meter rule, okay? Start with a meter rule. Now, a meter rule, as you can see in the diagram here, okay, we use it to actually measure just short distance, all right? Short distance. The laboratory wood, that's what is known as the uniform meter rule, which of course uses wood. That is 100 cm, okay? Short distance. Now this is just small graph meter rule. This is just it, all right? So now as you can see, there's something you notice about meter rule. Every measuring instrument, okay, have what is known as precision, okay, like precision, or you call it the accuracy. The accuracy is actually the least error, okay, or the highest accuracy you're going to get. Both error and accuracy, okay, is talking about precision, how precise your reading is, okay. What actually determines the precision of a particular, if you are being asked the precision, the accuracy, they all mean something, the least error. What determines all that in the measuring instrument? It is the smallest unit of the measurement in that, okay. As you can see in this meter rule, between the interval, each small unit, unit of the measurement, small line, as you can see, is 0.1. Okay, now let's see between 1 and 2. Okay, do I have 1? I have 2. Okay, before I get from 1 to 2, there are small intervals, okay, and each of these small intervals is 0.1. So if I have 1, I'll have 1.1. okay, the next is 1.2, the next is 1.3, 1.3 till I get to 1.9, then 2. Okay, so each one is actually giving you a space, okay. The least you can get is 0.1. So for a meter rule, the precision is 0.1, depending on the unit. So if it is in cm, okay, if that meter is measured in cm, that's 0.1 cm. If it's in millimeter, so I can just say that the precision is just 0.1 unit, okay, for a meter rule. All right, so that is the precision or the least accuracy you're going to get for a meter rule. Now let's look at other measuring instrument, okay. So we proceed. So length uses meter rule, okay, and of course there's one problem that we get anytime measurement is actually an error, which is common, okay, to the measurement in the meter rule. Is very common. I'm bringing it on the screen, okay. That error is known as parallax error. As you can see, I have 3 students here, okay, taking measurement. What is actually parallax error? Parallax error is actually the error you get when you look at a meter rule at a very slant angle, when your face is actually slant instead of looking directly downward. So in this measurement now, it is the student B that will actually get the right measurement because it's vertically looking downward to the meter rule, but C is looking from a slant angle, so he's making a mistake of just one unit, okay, and A is also making a mistake. So C will have an error in addition because of from the angle he's looking at, and A will have an error in subtraction from the actual reading because of the angle he's looking at. So parallax error is one common error that is actually common, okay. It's common with meter rule, so please take note of that in case you are being asked in the examination. So now let's look at another length measuring instrument, okay. So we have different measuring instrument for length depending on what you're looking at. So the next we're going to be talking about is a vernier caliper. All right, so now vernier caliper is used often to measure the external and the internal diameter of a round shape, okay, or round object. Let's use round objects. If the object is round, okay, and round, if you round hollow, please put it this way, round hollow objects, okay, round hollow objects. I mean, see, have space in between, okay. You can use that to measure internal. You can use it to measure the internal and the external diameter. I think I'm gonna give you an example of what I mean by that. All right, so we have that still on the note. So see, as you can see, there's a diagram here. I want to show you. Okay, let me show you directly from here. So this is actually shows a vernier caliper measuring a ball bearing, right? The external diameter. So you can also see how a vernier caliper, you can clip it, okay? Clip it around the shape you want to measure. You measure the diameter external. If you want to measure the internal, you clip it, okay, to hold the internal diameter, and of course you can take the measurement, okay, of the internal diameter. So please take note of that. And of course, this is the schematic diagram of a vernier caliper. Now a vernier caliper have two scales, okay. Of course, it has a jaw, we call movable jaw, where you move it to clip the object you want to measure. This is the object you want to measure, okay. So now it has two scales, right? The vernier scale, the one that is actually calibrated inside the movable jaw that you move, and it has the main scale, okay, that is on the main scale is found on the fist, okay, the fist jaw. We have the movable jaw and fist jaw, okay. So now when you move the movable jaw, all right, and the fist jaw, the point where the movable jaw and the fist jaw coincide, that is your take the reading. Now I'm going to illustrate that in details, okay. What are the how do we take reading using vernier caliper? All right, so that you will, once you see a reading that is being measured in vernier caliper, you understand it, okay. Here we go. There's a formula which definitely we need to. Then before then, okay, please take note of the fact that the precision of a vernier caliper is 0.01. All right, so I'm going to take an example, just an example will illustrate this measurement. Okay, so let's say you have been given these diagrams and you have been asked to take the reading or to tell what the reading is. Okay, here we go. Okay, so let me get the main diagram itself for the main question, right? Here we go. Okay, so now we have this. The length of the piece of glass below is measured, okay, using vernier caliper shown. So the length, we are looking at the length here. So now this is the diagram. This is the movable. This right here is the movable jaw, okay. This is the fist jaw. If I want to take this length, okay, the formula for the reading of a vernier caliper is just very easy, okay. So reading is just actually, the actual reading is gotten when you combine, okay, the main scale, which of course is found in the fist jaw, okay. Combine the main scale, then the main scale plus the reading of the vernier scale, okay, vernier scale. So if we look at this now, where am I taking the reading from the main scale? Look at the main scale here. This is 1, okay, this is 2 from the main scale. Then of course this is 1.5, the midpoint between 1 and 1.5. So I have, this is 1.6. So the main scale is giving me 1.6, okay, the main scale. Now remember there's a vernier scale, this one here, all right. Now plus vernier scale, how do I take the reading of the vernier scale? Okay, I'm going to count the number of interval to the point where the main scale coincide excuse me, the point where the main scale coincide with the vernier scale, as you can see, the main scale coincide with the vernier scale at the point number 2, as you can see here. That's where they coincide, and you count the number of units. Okay, 1, 2, 3, 4. Are you okay? And of course, we are told that a vernier caliper has a precision of 0.01. So each of these small vernier scale units is 0.01. Okay, so since there are 4 of it, all right, I'm gonna have 4 times 0.01. All right, so this is gonna give me 1.6. 4 times 0.01, that will give me 0.04. 0.4, right? 4 times 0.01, yeah, 0.04. Okay, so when you combine this is gonna give 1.64. So this reading is 1.64 millimeter. Okay, so I hope that is well understood. Okay, so that is a measurement from a vernier caliper. All right, so please take note of that. As we go to the other one known as the micrometer screw gauge. All right, so please take note of that. I take all the notes. I'll bring it to the screen. Okay, micrometer screw gauge. Now, this instrument is used mainly to measure very small lengths, like the thickness of a paper. Okay, so as I said, depending on the magnitude of the length, it needs a particular measuring instrument. Okay, now you know what thickness of a paper is, as small as it is. Okay, we use a micrometer screw gauge is what will really give you the accuracy. Okay, for a thickness or a very small ball bearing with greater accuracy than vernier caliper. So a micrometer screw gauge will measure small objects, giving you more accuracy than what a vernier caliper can give you. All right, so please take note of that. And this is the diagram, though it's not really showing well. Okay, so now take note of the accuracy and the precision for a micrometer screw gauge is 0.01. The same accuracy we have with a vernier scale, the same accuracy unit. All right, so now let's look at how we take the reading now from this. Exactly a diagram of reading of micrometer screw gauge. Okay, now micrometer screw gauge, if you look at from the diagram here, okay, has also the movable scale. Are you okay? And of course you also have the sleeve, which has the fixed scale, right? And though this is it's not looking much. So now looking at from the schematic here, there's a movable scale. The main scale, it has the main scale. This is the main scale. This horizontal is the main scale. Okay, as you take the main reading. All right, and then of course this one here is the movable scale that you rotate. Okay, and of course the reading of the main scale, the total reading. Okay, let me move this. Excuse me, so that I take the reading. This reading so that you understand how it works. Let me move this. Okay, no, now, so the reading of a micrometer screw gauge is still, we take the reading the same way we take that of a vernier scale. Okay, we take the reading from the main scale. Okay, and of course with the movable scale. Okay, so here we are. From the main scale, we have 5.5, and of course, we take the movable scale reading at the point where the main scale coincides. So we count the number of units from that point. And look at where it coincides. Okay, so remember, we have if you wanna, okay, we don't need to count that. You are being given this point is 30. Okay, so if this point is 30, that means 1 unit. Then 1 unit after 30 will be 31. All right. And don't forget that each small unit, this small intervals is 0.01. So we have 31 of them. So 31 times
0.01. Of course, this is gonna give us 5.5. Then when you multiply this by that, you're gonna have 0. Okay, 0.31. Yeah, if I'm not mistaken. Okay, yeah, 0.31. Which of course, when you add up, okay, you're gonna have 5.81, right? So you can confirm that with your calculator. Just confirm that. All right, so that is it, and we proceed. Yeah, let's see what we have. Okay. Okay, so what's the next thing we're actually coming to the, so we'll talk about the measurement of mass, right? Measurement of mass, right? All right, let me take it up to the screen. All right, so here we are. So mass is the quantity of matter in a body, while weight is the measure of gravitational pull, because students used to confuse between mass and weight. Okay, mass versus weight. All right, mass is actually the quantity of matter contained in a body. Okay, while weight is the measure of gravitational pull on a body. All right, now the relationship between mass and weight is shown below. Okay, so for you to actually convert mass to weight is always given as mass times acceleration into gravity. That is why weight, W, okay, is, if you want to convert mass to weight, you just multiply by G. So weight is always mg. Are you okay? So now that is why there's a difference between the two. There's actually difference between the two, clear difference. Okay, now let me mention the clear difference. First of all, weight is actually is a force, right? Weight is a force. You understand? Mass is not a force. Okay, so that is why weight is measured in Newton. Please take note of that. And that is how you convert it. So if you have mass and you want to convert it to weight, multiply by G, okay, it will convert to weight. So of course, for every force is a vector quantity. All right, mass here is a scalar quantity. All right, now if you go to the note, you're going to see a table that actually differentiates between mass and weight. All right, okay, but the important thing we need to know about this is that the measuring instrument of mass, okay, is we use what is known as chemical balance, chemical or beam balance. Okay, chemical or beam balance. Okay, that is the measuring instrument. And of course, chemical balance actually operate using the Press-Plot moment. Okay, operate with the Press-Plot moment. Press-Plot moment is simply the principle of balance. Okay, where a beam is being pivoted at the center. Okay, a mass is being placed, a known mass is being placed at one end of the beam. Okay, while the measured mass is placed at the other end. Okay, now the amount of rotation you get, right, from the balance point. Okay, when there's the balance point shows you that the mass at both sides of the pivot, yeah, they are equal. Okay, but when there's a rotation either to the left or to the right, will tell you, okay, the amount of weight you have, the amount of unknown weight or unknown mass you place at the other side. So that is basically how all this work. Then we now, the last but not the least, the note. If you go through the note of this, of course, which of course when you download the textbook, which is also part of the platform, okay, you get to read all those things, read about them. They are well explained. Okay, so I think so far so good. We have gotten a very good insight, okay, in this topic, and I'm very sure that with what you have gotten, you can actually appropriate it, go through it again, and of course answer examination questions. So what you're going to do is that in the next video we are going to look at typical examination questions, then we'll answer them. All right, see you in the next video. Thank you very much.